That's right, Harry Potter. I'm sure we all remember this scene.
Wizard's most rudimentary skills is levitation, or the ability to make objects fly. Do you all have your feathers? Good. Now, don't forget the nice wrist movement we've been practicing. The swish and flick. Everyone? The swish and flick. Good. Oh, and enunciate. Wingardium Leviosa. Off you go, then.
Wingardium Leviosa. Wingardium Leviosa. Wingardium Leviosa.
Stop. You're going to take someone's eye out. Besides, you're saying it wrong. It's Leviosa, not Leviosa.
You do it then if you're so clever.
Go on.
Wingardium Leviosa.
Wingardium Leviosa.
Oh, well done. See here, everyone. Miss Granger's done it.
Some of us may be able to completely relate to Ron. I mean, just look at Hermione. Just look at her. I bet we all wish we had these spells in our engineering classes. It may seem like something that can only happen in Hogwarts, but feedback control systems can help us levitate some of these objects. To levitate an object, we must completely overcome the force of gravity. We can fight gravity's force with the force of an electromagnet, but what happens if that electromagnet overcompensates? That's where the steady state position comes into play, and it's very important. As you can see in the equation in this green box, the steady state position actually does correlate with the steady state current from the solenoid. So that can actually be pretty helpful. Also, notice how it actually looks like a mass spring systems equation. That can also become pretty helpful with actually trying to find out how we can model this entire system. That's why a Hall sensor is so valuable here. A Hall sensor will sense that magnetic force and output a voltage. So if your mass gets too close to the solenoid, thus the magnetic force is increased, then the voltage will decrease. And if the mass gets too far from the solenoid, thus the magnetic force will decrease, then the voltage will increase. And this will help it come to the steady state position. Or does it? When looking at our system, we must realize that this is a theoretical system. That means that the mass will not just experience the two forces shown here. Our mass will oscillate until it reaches a steady state position. Using the Hall sensor alone, we will reach some problems with the timing. This may cause our system to... Okay, maybe it won't explode, but the sensor won't be able to change the voltage quick enough. Let's look at the stability of our system. The location of our poles will tell the stability of our system. One of our poles is in the right-hand plane, which is not what we want. We can use the PD controller to bring this pole into the left-hand side, making our system more stable. These poles came from our process transfer function, H of S, which we can modify to include a PD controller. We use the Routh-Hurwitz method to find the range of our PD controller. This simple block diagram shows how we will integrate each element into our system. Now let's look at that process. Now let's focus on that process. This is our process at its simplest. The L is represented by the solenoid. And then we have our two resistors. One is 1 kilo ohm and one is 330 ohms. We also have two diodes. One is an LED, but the other is an HER207 diode. We also have a transistor. The transistor is an IRFZ44N transistor. And we also have our Hall sensor, which is an A3144 sensor. All of this can be tested separately from our controller, which we actually did. As you can see, we hooked up our entire system separately from our controller, and we wanted to really focus on getting our Hall sensor to actually work. You can see each element hooked up to our breadboard for testing here. This is before it goes into the PD controller, so we just wanted to test to see if it all worked, and it actually surprisingly did. Then we hooked in our controller, and we were able to actually get something a little bit strange. This is what we came up with. It may not be perfect, but it is something. So yeah, I guess we can't all be Hermione, but at least we tried. And at least we didn't end up like this kid.